Okay, we'll get back to section 6.2. We're talking about volume using the disk and washer method. I haven't talked about the washer method yet, but it's really just the disk method being used twice. Okay, so suppose that we have a washer, okay, a circle within a circle, and suppose that the smaller circle has a radius of little r units and the big circle has a radius of capital R units. Well, the area of this washer would be with the area of the bigger circle minus the area of the smaller circle, right? You're removing the unwanted space. Now suppose that we use several washers to make a cylinder that has a hole in it. Okay, if we want to find the volume of this cylinder with a hole in it, we would take the area of each washer and then multiply by the width, whatever the value of W is. Okay, and now we're going to extend this idea to a curve being rotated about about an axis, which is what the disk method was all about. I've described the washer method here, and that's also on the sheet here that I've been referring to on occasion. So the washer method, if the object generated by revolving a curve about an axis has a hole, then you're going to use the disk method twice in order to remove the unwanted space. Okay, so let's take a look at some examples. In my first example here, suppose that we want to find the volume of the region that is bounded between y equal the square root of x and y equal x squared. That is rotated about part A, the x-axis, and then part B will rotate about the line x equal -1. Okay, I'll set up part A here first. So I've drawn these two curves, y equal x squared and y equal the square root of x, and here's the bounded region that I've got shaded that we're referring to. Okay, we're going to rotate that about the x-axis. Well, if you can imagine rotating this about the axis, you're going to have something with a little hole in it there, or there's some unwanted space. Okay. Now, let me first rotate the region that would be underneath the curve y equal the square root of x and above the x-axis and between 0 and 1. By the way, because I'm rotating it about the x-axis, I know right away that I'm going to have an integral set up in terms of x. Okay, and so that's going to be my variable of integration. We're going to have pi times an integral when we calculate v, and the conditions on x here is that x is going from 0 to 1. And okay, so I'm going to begin by looking at this disk that is from y equal the square root of x to the x-axis, and we'll rotate that about x. Remember, it's the top curve minus the bottom curve. So we're looking at the square root of x minus the bottom curve is y equals 0 squared. Now I don't want that complete region rotated about x. I want to remove, so minus, the region that would be below y equal x squared and above the x-axis. Well, again, top curve minus bottom curve, right? I'm going to take x squared minus y equals 0 squared. Okay. Now I'm all set up, and now it'll be just a matter of calculating this integral here. So we're going to have x minus x to the fourth inside the integral. The antiderivative then would be 1/2 x squared minus 1/5 x to the fifth, and we're evaluating this from 0 to 1. Pi is a multiplier. And when I plug in 1, 1/2 minus 1/5 is 3/10. When I plug in 0, I get 0. So 3 pi over 10, that would be the exact answer. That would be the exact volume of this three-dimensional object. Okay, part B, suppose that we're going to rotate this region now about the line x equal -1. Okay, so if I rotate this about the vertical line x equal -1, again, I'm going to have a three-dimensional object that has a hole in it. So I'll want to use the washer method. Now also, because I'm rotating this region about a line that is parallel to the y-axis my integral setup, everything about it is going to be in terms of y. Okay, so we're going to have pi times an integral, where everything about the integral is about y. Now the conditions on y for this enclosed region is that y is going between 0 and 1. Okay, now that's the same bounds that I had on part A, but again, we're talking about y this time, okay? Y is also ranging between 0 and 1. Now, let's first rotate the region that is between x equal negative 1 and y equal x squared about the line x equal negative 1. Okay, now you want to take the right curve minus the left curve. The right curve is y equal x squared, but I don't want to write x squared, okay, because everything has to be about y. If y is equal to x squared, x would be equal to the square root of y, would be the right half of this parabola. X equal negative the square root of y would be the left half. We don't have the left half showing there. Okay, so x equals the square root of y would be the right curve minus the left curve. The left curve is x equal negative 1. Square that. Okay, and that would get you this region rotated about x equal negative 1. Now I don't want that entire region to be rotated about that vertical line. I want to remove the unwanted space. Okay, so I'm going to subtract the region that would be between x equal negative 1 and y equal the square root of x. Well, again, it's going to be right curve minus left curve. Okay, so the right curve is y equal the square root of x, but I don't want to write square root of x there, right, because it's got to be about y. If y is equal to the square root of x, then x would be equal to y squared. So the right curve would be y squared minus the left curve would be x equal negative 1. Okay, square that, stick a dy at the end, and we're all set up now to find v. So I'll need to FOIL out these two parts. I've done that in the next line. And also I've distributed this negative here into the three terms in that second expression. 1 minus 1, those cancel. And I don't have any other like terms, so I can go to the antiderivative next. You're going to have pi times 1/2 y squared plus 2 times y to the 3 halves times 2/3 would be 4/3 y to the 3 halves, and then minus 1/5 y to the 5th, and then minus 2y cubed divided by 3, that'd be minus 2/3 y cubed, and we're evaluating this from 0 to 1. Okay, plug in the bounds. When I plug in 0, all these terms are going to be 0, you know, for my lower bound, but when I plug in 1, I'm going to have pi times 1/2 minus, let's see here, it's going to be, it should be a plus 4/3. Sorry about that. Plus 4/3. And minus 1/5 minus 2/3. Okay, and then when you simplify what you see here, I'm getting 29 pi over 30 as the exact volume of this three-dimensional object. Remember that you will always have positive numbers for all the calculations in this section. Actually, the first section, 6.1, 6.2, and 6.3, and then most of 6.4 is going to be positive also. But keep that in mind. Okay, here's another example. Suppose that we want to rotate the bounded region that is from the curves y equal x squared plus 1, y equals 0, x equals 0, and x equal 1. I've drawn that region. We're going to rotate that about the y-axis, and that's part A. Part B, we're going to rotate this about the line y equal 3. Part A, I'm going to rotate this region about the y-axis. Now, in rotating this about the y-axis, you'll notice that I'm going to create a 3D object that's kind of got like a cup shape in it. And now this bottom part that's going from 0 to 1 on the y-axis, you can use the disk method. Like there is no hole in that part that's being rotated about the y-axis. Now the top part that is going, for when y is going from 1 to 2, when you rotate that about the y-axis, there's going to be this hole, this cup-like form that we want to remove. So in this particular setup here, I'll have two integrals that I'll need to add together. That is the volume of the lower half and then the volume of the upper half. That'll get me the total volume, V. So if we first, and by the way, since I'm rotating this region about the y-axis, everything about these two integrals here is going to be about y. Okay? And, well, let's see, for the lower half, y is going from 0 to 1. Right curve minus left curve. The right curve is x equal 1. The left curve is x equals 0. 1 minus 0 squared dy. That'll get me the volume of that cylinder that you see in the lower half. Okay, and then I'm going to add to that more volume, which is going to be the part where I'm going from 1 to 2, then on the y-axis. Again, everything is going to be about y since I'm rotating this region about the y-axis. Anything about rotated about the y-axis or something parallel to that means that your setup is going to be about y. Okay, anything rotated about the x-axis or something parallel to that has to be about x. That's me part B. That second integral, like I said, the bounds are going to be going from 1 to 2. I see there. And now we'll use the washer method on this part. I'm going to start by rotating the region that is between x equals 0 and x equal 1 about the y-axis. So, from what I had before, that's going to be 1 minus 0 squared. I don't want that entire region to be rotated around. I want to remove the unwanted space, that is the space between x equals 0 and the parabola y equal x squared plus 1. Now, if y equal x squared plus 1, then when you solve this for x would be the square root of y minus 1. It'll happen, here and there where you'll have to solve an equation for the other variable before you plug in that expression into your integral when you're getting set up. So be sure that you're careful about that and you're watchful of that. Okay. So the right curve is the square root of y minus 1, and then minus the left curve. The left curve is x equals 0. And I want to square that. Stick a dy at the end, and so here would be the setup that we would need to get us the total volume then of this object. Okay, let's compute. So we're going to have pi times the integral going from 0 to 1 of dy. That's going to be pi times y, which is being evaluated from 0 to 1, or that'd be pi. Okay, so that's easy enough to get. Plus the second integral, okay, you're going to have 1 minus y plus 1. 1 plus 1 is 2, minus y, and then when you find the antiderivative of that, you're going to have 2y minus 1/2 y squared. Be sure that you remember to put pi in front of that, and we're evaluating this from 1 to 2. Okay, plug in the bounds. So when I plug in 2, I'm going to have 2 times 2 is 4, okay, minus half of 4 is 2, okay, and then minus, when I plug in 1, I'm going to have 2 minus 1/2 there. And when you simplify, okay, it's going to be 2 minus 3/2 is 1/2. Pi plus 1/2 pi would give you 3/2 pi then is the answer. All right, now I put a star by this because this is one option that you could consider to find the volume in this problem. We're going to look at the same problem in the next section, and there's going to be perhaps a better way to do this problem. I wouldn't say a better way because this, what we had here isn't overly difficult in my opinion to get set up. But so we'll look at another option there in the next section. And I'll refer back to the star then when we talk about the cylindrical shell method there in the next section. Okay, part B, I want to rotate this region about the line y equal 3. Well, since I'm rotating this region about a line that is parallel to the x-axis, everything about my integral has to be in terms of x. The conditions on x for this enclosed shaded region is that x is going from 0 to 1. Okay, now I'll use the washer method in my setup here. Let's first calculate the volume of the region that would be rotated from y equals 0 to y equals 3. Okay, top curve minus bottom curve. So the top curve is y equals 3. The bottom curve is y equals 0. Square that. Now I don't want that entire rectangular region to be rotated about y equals 3. I want to remove the space that is between y equals 3 and the parabola. All right, so I've got a minus. Again, it's going to be top curve minus bottom curve. The top curve is y equals 3. The bottom curve would be y equal x squared plus 1. Top curve minus bottom curve. Okay, you're squaring that. Stick a dx at the end, and now we can compute. So we're going to have the integral, pi times the integral going from 0 to 1 of 9. And then, let's see, 3 minus 1 is 2. 2 minus x squared squared. I'm foiling that out on the next line. And then 9 minus 4 is 5. Okay, so we need to integrate 5 plus 4x squared minus 4x to the, or minus x to the fourth, going from 0 to 1. And so that's going to be pi times 5x plus 4/3 x cubed minus 1/5 x to the fifth. We're evaluating that from 0 to 1. Plug in the bounds. When you plug in 1, you're going to have 5 plus 4/3 minus 1/5. That should be 92 over 15 if you were to check that. Okay, and we're plugging in 0, which all three of these terms are going to be 0. So I'm getting 92 pi over 15 as the exact volume of this three-dimensional object. Okay, so here's the homework problems on page 446. I'd like you to look at those, and we'll talk about the shell method in the next section, which is just a continuation of volume calculations.